Greetings everyone, I am Shistiyah binti Mohamad Halid and I am honoured to present our research title, Unsupervised Anomaly Detection using Segmentation and Object Localization for Real-Time Surveillance Application. This work is the result of collaborative effort with my co-authors from University Technical Malaysia Melaka and Zhang Ocean University. In today's presentation, I will walk you through how our framework combines computer vision and AI to detect and localize anomaly in real time without the need for extensive label, data, or manual supervision. Let's begin by understanding the need for smarter anomaly detection system. Anomaly detection isn't just a technical challenge, it's a real-world necessity. Whether it's ensuring public safety through surveillance, monitoring patients in healthcare, maintaining quality in manufacturing, or even preventing accidents in transportation. Identifying unusual events quickly and accurately can literally save life and resources. But how do we detect anomalies today? Often we still rely on manual monitoring, someone watching CCTV feeds for hours, or rule-based algorithms that are programmed to look for specific triggers, like if someone enters a restricted zones, sound an alarm. This method have serious limitation. Humans get tired. It's called vigilance fatigue and can miss critical event. Rule-based systems are rigid and they can adapt to new or unexpected situation. Both approaches often lead to delayed response and struggle in dynamic real-world environments. That's exactly why we set out to design a system that overcomes these barriers. We wanted something that works in real time, learn without heavy human supervision, and adapts without needing constant retraining. So in the next slide, I will walk you through how our proposed framework, an unsupervised vision-based system that not only detect anomalies but also can localize them precisely in video stream. Now let's look at how our system works. I will explain high level view of our proposed framework and end-to-end pipeline designed for real-time unsupervised anomaly detection. We start with live video stream. This could be CCTV feeds, drone footage, or any real-time visual input. The system processes frames sequentially, ensuring no lag in detection. The first step of this is foreground segmentation. Here we separate moving objects from static background. This helps us focus only on relevant activities and reduce computational load by ignoring unchanging scenes. And next, we move to object detection and localization. Using the state-of-art models like mass-to-former, we not only identify what objects are present, like peoples or vehicles, but we also identify precisely where they are. The core intelligence lies in the anomaly inference engine. Unlike traditional system, ours doesn't rely on labeled abnormal examples. Instead, it learns what normal looks like over time. Any significant deviation from learned patterns is flagged as anomaly, all without human supervision. And finally, the output layer delivers clear, actionable insight. Anomalies are highlighted with visual overlays like masks, making it easy for operators to understand what's happening at a glance. Alerts can also be logged or sent as notification. Traditional anomaly detection relies on supervised learning, which means you need to feed the system thousands of examples of both normal and abnormal behavior. That's not only time consuming, but also limiting because you can't possibly label every type of anomaly in advance. Here's the key difference. Supervised method require labeled dataset, struggling with unseen anomalies and need retraining for every new environment. Our unsupervised approach, on the other hand, learns only from normal data. It builds a baseline of what expected, and anything that deviates significantly is flagged. No labels, no retraining, and no predefined rules. In this practice, this means our system can deploy in new location, let's say a factory floor or a hospital corridor. And within a short time, it learns a typical activity patterns. From then on, it can detect faults, intrusion, equipment malfunction, and or any unusual event without ever having seen that specific anomaly before. Our methodology brings together two powerful models, master-former for precise visual segmentation and blip for deep semantic understanding. This combination allows us to detect anomalies not just by how things look, but by what they mean in context. First, master-former handles the where. It performs instant segmentation, creating pixel-perfect masks around every object in the scene. whether it's person or vehicle or an unintended bag. Mastoformer isolates it with high precision, and this will give a spatial accuracy. But information alone isn't enough. That's where BLIP comes in. BLIP is a vision language models that add semantic understanding. It looks the same scene and generate it look at the same scene and generates contextual description like a group of people walking orderly or a person running against the crowd. And then we use mask to formers and mask it with blip segmented labels. Each segmented object gets not only bounding box and mask, but also a contextual tag. This allows us to detect anomalies that are semantically unusual and not just visually different. For example, a person standing still in a crosswalk might be flagged even if they look normal visually. But why we use both? Because real-world anomalies are complex. Mastoformer answer where is it and what shape is it, and Blip answer what is happening and is it normal. Together they give us a complete picture of both spatial and semantically. This fusion happens in real time, with Mastoformer handling the heavy visual processing and Blip adding lightweight semantic analysis. The result is a system that understands a scene like a human would, seeing both object and their meaning. And now we this powerful dual model approach, and we will measure the effectiveness with evaluation metric that quantify both spatial accuracy and semantic relevance. So how do we know it works well? We can't rely on intuition. We need hard quantitative metrics. That's why we evaluate our system using two complementary benchmarks that measure both spatial precision and detection reliability. First, with MIOU, mean intersection over union. This measures how accurately our segmentation must match the real objects. Imagine drawing a shape around a person. MIOU compares our drawn shape to the actual person outline. And second, MAP, mean average precision. This is the gold standard in object detection. It doesn't just ask, did you find it? But how confidently and consistently did you find it across different scenes? Confidence levels. A high MAP means our system rarely misses anomalies and rarely raises false alarm. Together, these metrics give us a complete picture. MIOU ensures we know exactly where the anomaly is, and it is critical for application. And MAP ensures we can trust the detection, that we are not missing real threats or crying wolf. Here you can see how IOU is calculated visually and what a strong precision recall curve looks like for MAP. In practice, our system aims for high score in both because in real world surveillance you need both precision and reliability. Our system achieved an MAP of 0.413 across IOU threshold from 0.5 to 0.95. More practically, at the typical IOU threshold of 0.5, we reached 0.621. That means over 62% of our detected objects are correctly identified and accurately localized. Breaking it down by object size, we see expected pattern. Large objects are detected excellently at 0.536 MAP. Important since many anomalies like fallen person or abandoned items are sizable. Medium objects perform solidly at 0.442. Small objects are more challenging at 0.255, which is common in crowded scenes but remains detectable. Recalls tell us how many actual anomalies we capture. Our best recalls 0.577, and for large objects it's 0.719, meaning we miss very few significant threats. And this will balance between precision and recall because it is crucial for real world trust. We are currently finalizing our segmentation MIOU evaluation, which will give us pixel level accuracy metrics. However, this detection results already confirm that our framework accurately localize anomalies, and the first critical step in which is the first critical step in any surveillance system. So these numbers mean our system can reliably detect and box anomalies in diverse conditions, with particular strength in spotting the kinds of events that matter most in safety and security application. These quantitative results combine our qualitative observation, which will give us confidence that our unsupervised mass-to-former combined with blip approach is not just theoretically sound but practically effective. At this stage of our project, we focus on qualitative validation and framework development. while full quantitative benchmarking is clearly demonstrate the viability and promise of our hybrid approach. In practice, our system is already segmenting objects accurately, localizing anomalies in real time, and thanks to blip understanding semantic context, it does not just detect a person on the ground, it understands whether that's normal sitting or a potential fall. You can see how Master Former cleanly isolated each person and how Blip adds descriptive text. When anomaly occurs, like someone in danger, the system highlights it immediately with both mass and meaningful label. We have observed several key strengths. The system adapts quickly to new environments, run efficiently even with two models, and produce clear interpretable outputs, which is crucial for real-world operators who need to trust and act on system alerts. Even at this stage, it is clear that combining mass to former for precision and blip for understanding creates a powerful foundation for unsupervised anomaly detection, one that is visually accurate and context aware and ready for real world refinement. Where can this technology actually be used? The answer is almost anywhere visual monitoring is needed. Our framework isn't just a research prototype, it is designed for real world impact. In smart civilians, imagine a system that doesn't just record footage but understand it, flagging a person loitering where they shouldn't be or detecting a crowd forming too quickly. And in industrial setting, it will spot a worker without safety gear or a machine leaking fluid before it causes harm. In healthcare, this isn't just about a civilians, it's about care. A system that detects a patient falling or wandering into restricted area can alert staff instantly. In retail and smart spaces, it could manage queues, detect slip and fall accidents, or even help prevent theft, all while preserving privacy. But we are not stopping here. Our future roadmap is still split into short-term and long-term goals. In short term, we are focusing on quantitative validation, edge optimization, and integration with existing systems, making it deployment ready. In long term, we envision multimodal system that combine video with sound, thermal, or LiDAR data. We are exploring federated learning to train across location without sharing sensitive data and autonomous drone integration for dynamic civilians in large or remote areas. Ultimately, Ultimately, our goal isn't just to replace human oversight, it is to augment it, to give security guards, nurses, factory managers, and safety officers a tool that sees what they might miss, understand context, and acts in real time. A tool that makes space safer, smarter, and more responsive. That brings us to the end of our presentation. We have introduced an unsupervised real-time anomaly detection framework that combines mass to formal for precise segmentation and blip for semantic understanding, designed to scalable, adaptable, and practical for real-world deployment. Thank you again for your time and attention.